Hello, welcome back. The title of this lesson is called Graphs of the Tangent and Cotangent Functions. And this is part one. So this is a single sheet of paper lesson. We're going to do a computer demo here in the very beginning to show you the graphs of these functions and play around with them and shift them around and things like this. But don't lose sight of the big picture. We have sine, cosine, tangent, and then cotangent, and then secant, cosecant. By far, the most important trig functions we've already covered, those are the sine and the cosine. Most students can understand that, I think. I mean, we work with it and we get it done. But when we get to the tangent and the cotangent, a lot of students get really confused because the graphs of those functions, they have asymptotes and they just look weird. So what I want to do is remind you at the very beginning that the tangent function is defined by definition to be equal to the sine of whatever angle you're talking about divided by the cosine. So tangent of an angle, either theta or x, whatever variable you're using, is equal to sine of that angle divided by the cosine. Why is that? I'll write it on the board in a minute, but the reason why is because if you remember back to what the tangent is, it's the opposite side of a right triangle divided by the adjacent side. But in the unit circle, the opposite side of the triangle is what we call the sine of the angle. And the adjacent side of the triangle in a unit circle is what we call the cosine. So opposite over adjacent, sine of the angle divided by the cosine of the angle. And we have a new name for that. We call it the tangent of an angle. So what I would like to do is jump to the computer. We'll understand the graphs. We'll look at how they function and behave, how they get shifted around. We'll come back to the board and we'll continue learning about tangent and cotangent. All right, welcome back. So here we are at the computer. We're going to talk about tangent, but before we do that, let's refresh our memory on what the sine is because we're going to need it in just a second. Here's the sine function, starts at 0, it goes up to a maximum of 1, a minimum of -1, and it goes back to its starting point. So 1 period for the basic sine function is 2 pi. And I have a note to myself to remind you of that the period of the sine function is 2 pi. In other words, 1 cycle of the basic sine function occurs over 2 pi. Now let's refresh our memory. What does the cosine function look like? Well, it's very similar. It's just a shifted sign, but the cosine starts at a maximum of 1, goes down to a minimum, and back up to its starting position. Again, it takes one cycle, takes 2 pi. So I have a note here that the period of the cosine function is 2 pi. So the period of the sine and the period of the cosine, they both have a period, which means they both begin to repeat after 2 pi radians. Now let's talk about the tangent function. This is a graph of the tangent function. I told you it looks a little funny. It doesn't look like the sine and it doesn't look like the cosine. And that's because the tangent function is the sine of the angle divided by the cosine of the angle. And it produces this funny graph. We're going to talk about it in a second. Before we talk about why it has this shape, I just want you to look at what its period is. So it starts down here. See, this goes down, and if you were to continue graphing it, it actually goes to -infinity down here, and then it traces out a path to positive infinity. Each one of these little curves are basically going from positive infinity down to negative infinity. I'll tell you why it does that in just a minute. But if you look at when would this graph repeat itself, notice that if it goes up and then up to positive infinity, then down here it begins to start over again. So one of these little s's here is called 1 period of the function. So here at -pi/2, we begin one cycle, and we end that cycle up here at a positive pi/2. So what does this mean? From -pi/2 to pi/2 is 1 cycle. And if you think about that, you have a distance of pi/2, another distance of pi/2. The total distance over here is actually pi. So the period of the tangent function is not 2 pi. The period is actually 1 pi. So it's half the period. So just to refresh your memory, the cosine and the sine both begin to repeat themselves after 2 pi, but the tangent function, which is the division of the sine divided by the cosine, does not have a period of 2 pi. It has a period of half of that, a period of pi radians, okay? Now let's talk about why it has this shape. What we're doing when we plot this thing is we're literally taking the sine of the angle and the cosine of the same exact angle and just dividing those numbers. So if you go over here, for instance, here's the cosine and here's the sine. The tangent is defined to be the sine divided by the cosine. So let's go over here and look at pi/2, for instance. The maximum, the local peak of this curve. The sine of this angle is 1, and the cosine of the same angle at pi/2 is 0. What happens when you divide by 0? Well, in algebra, lower level algebra, we say it's undefined, but really, we know that as this thing gets closer and closer to 0, we're dividing by something closer and closer to 0, so it drives the result to infinity. That's why we get these infinities right here. It's because it's sine divided by cosine, and as cosine, as we evaluate the cosine around the unit circle, sometimes the cosine of the angle is 0, and that means that we divide by 0, and so it goes to infinity. So then you might want to say, well, why does it sometimes go to positive infinity, and then other times, like down here on the other side, it's actually over at like negative infinity? Why does it switch like that? Well, think about what's going on. Here we're dividing to take the tangent, sine of this angle, which is 1, or very close to 1, and we're dividing by cosine. Now let's pretend that we're actually at an angle slightly lower than pi over 2. That means we're dividing by a very small number, but it's positive. So we're going to get something very close to positive infinity. But once we cross the line over here to the right side of pi over 2, we're dividing by a very small number, which is actually negative. So when we divide by a small number that's negative, it drives it to negative infinity. That's why it's approaching positive infinity up here, but then it has this discontinuous jump down to negative infinity. That's because the cosine of that angle is switching from positive to negative, and it's crossing through 0. Now, I don't have them drawn on this curve, but we can draw dotted lines here and call these vertical asymptotes between all of these positive and negative infinities, because the function here never gets to infinity. It just approaches it, and it never gets to negative infinity. It just approaches it there. Well, let's take another point. So we've done pi over 2. Let's look at this point here. When x is equal to 0, or theta is equal to 0, what is the sine of that angle? It's 0. What is the cosine of this angle? 1. What is 0 divided by 1? You get 0. And so the tangent function is indeed 0 at the origin. So you can see that we have to cross through the 0 point. We have to get up to positive infinity, and the path that it traces to get there is this little curved path here. And then, of course, as we go into the negative angles, it's getting closer and closer to negative infinity, because at negative pi over 2, what is sine divided by cosine? Well, cosine of negative pi over 2 is getting very, very close to 0, but it's still a very small negative number. So I'm dividing by 0, but really it's a very small negative number. So it's driving this thing to negative infinity. So this pattern repeats itself. Every time we have one of these asymptotes here where they go to infinity, those are the angles where the cosine part of this function is 0. That's why the infinity happens. And then the other points in between, it's crossing over the origin at the positions where the sine of the function is 0. So sine of 0 is 0. Look at pi right here. Let's look at pi. An angle of pi, the sine of pi is 0, and the cosine of pi is -1. When you divide those numbers, you still get an answer of 0, so it crosses through 0 again. So the tangent function sweeps out these little S-curves that have these vertical asymptotes. The period of the tangent function is not 2 pi. The period is actually a single pi. And notice that the tangent function, the way that you would sketch it, you would start at negative pi over 2, and then you would kind of go through the origin, and then you would go up to infinity up here at pi over 2, and then the pattern would just continue to repeat every pi radians. Now that's the tangent function, sine divided by cosine. Now if you remember from trigonometry, the cotangent function, when you write down the trig rainbow I taught you, the cotangent is defined to be 1 over the tangent. But again, tangent we know is sine over cosine, so you can think of cotangent two different ways. Cotangent, you can think of it as just 1 divided by the tangent function, or you can think of cotangent to be cosine divided by sine, because 1 over tangent would be cosine divided by sine. But notice what this curve is. It's this exact same shape, but it's slightly different. Notice that it's shifted with respect to the cotangent. We still have, or to the tangent, we still have the vertical asymptotes, but notice the vertical asymptote is here on the y-axis and then here at pi, but up here, it wasn't there. It was shifted over, it was at negative pi over 2 and positive pi over 2. Why is that the case? Because if you look at the tangent function, what is 1 over infinity? This is up infinity right here. What is 1 over infinity? It's 0. So where the tangent function is infinity, 1 over the tangent function should give me 0, and that's why it's a 0 here at pi over 2. If we go here to the origin, here we see the tangent function is 0. What is 1 over 0? 1 over 0 should be infinity. And so that's why we get infinity at the origin. The reason why we have the discontinuous jump is the same reason as before. Because here, when the tangent function is 0, if I'm a little bit to the right of the origin, then I'm dividing by a really small number that's positive, so it'll give me positive infinity. But on the other side of the origin, I'm dividing by a really small number that's negative, so I'm going to get negative infinity. So I have this discontinuous jump from positive infinity to negative infinity, again, a vertical asymptote. But notice the period of the cotangent function is still pi, because you can see that you have one repetition here going from, this is 0 going to pi. That's one repetition. Another repetition takes another pi. So just to kind of slow down and catch our breath before we go any farther, we have the sine function, which is a period of 2 pi. We have the cosine function, which is a period of 2 pi. We have the tangent function, which is the sine function divided by the cosine function. So literally at every point, if you take the value of the sine curve and divide by the corresponding value at the same position on the cosine curve, sine divided by cosine, you divide those numbers and plot it, you will get this shape. The infinities arise because sometimes the cosine of the angle is 0, and the reason it jumps from positive to negative infinity is because of the crossing point from positive to negative, as I said before. And then, of course, it crosses through 0 at the positions where the sine of the function gives you a 0, drives it to 0. We get these funny S-curves. And then we can think of the cotangent function being the inverse of that. So we can just literally take the tangent function and take 1 over that and arrive at the cotangent function here. And we can also think of it as cosine divided by sine. So you could also recover this curve by going here and picking any point on the cosine curve and then dividing it by the sine. For instance, let's take a look here at the origin, 0. The cosine is 1, but the sine is 0. So what's 1 divided by 0? Well, that's infinity. And the cotangent function goes to infinity here at the at when x is equal to 0. So you can think of the cotangent being 1 over tangent. You can also think of it as being cosine over sine. Either way, you get this family of curves. The cotangent curve has a period of pi, not 2 pi, pi. Now what I'd like to do is put them both together. You see this kind of curve a lot in textbooks. I personally find this nauseating, but putting them together does in some ways help you visualize. You can see the tangent in blue here starts at negative pi over 2, negative infinity, and goes up to infinity at positive pi over 2. And then it continues to repeat itself, going from negative infinity to positive infinity. And the gold curve is the cotangent. It's 1 divided by the blue curve. So you can see where the blue curve is infinity right here, 1 divided by that would be 0, and that's why the cotangent is 0 here. Look over here at the origin. 1 divided by 0 is infinity, and that's why we have the infinities here. Again, sometimes it's very close to 0, but being negative, sometimes it's very close to 0 being positive, is going to give me these negative infinities and positive infinities like here. But the end result is the cotangent function is kind of a flipped over version, so to speak. It still has a period of pi, but it is shifted a little bit with respect to the tangent function. Okay, now, if that doesn't bake your noodle enough, now we want to start talking about how do these things get shifted. Now, this is the good news. The good news is you already know how the shifting works for tangents and cotangents because it basically behaves the same as it does for the sines and cosines. This is a tangent function. It is exactly what I've already drawn as a tangent function. Now, if we add something on the outside, what do you think is going to happen? Well, if I add numbers on the outside, all I'm going to do is shift the tangent up that many units because I'm evaluating the tangent function, and then after I do that, I'm adding the number 4. So all the crossing points and everything just gets shifted up by whatever the constant is on the outside. If I make that constant on the outside negative, what do you think is going to happen? It's basically subtracting, and it shifts the curve down. So this is just like shifting sine and cosine up and down. When you add a number on the outside of the tangent function, it shifts it up and down, just like you would expect, okay? Now what happens instead of shifting it up and down if we change the coefficient in front of the tangent? Remember, that's how we change the amplitude of a sine and cosine function. When you change the outside coefficient, what you're doing is you're making the graph steeper. It still approaches infinity and negative infinity, but when you increase the multiplicative constant, then whatever you get for the tangent gets multiplied by 5. So it's like you grab it with your hands and you stretch it out in the vertical direction. You see, this is a normal tangent. And then as you multiply the normal tangent by numbers, then you're just making it steeper and steeper. And if you start multiplying by negative numbers, then the thing is going to flip over and give you kind of like S's that are reversed because then you're flipping the tangent curve upside down, essentially. So that's what a multiplicative constant on the outside of a tangent does. It just makes the little S part a little bit steeper. All right, finally, what happens if we change the coefficient on the inside of a tangent here? Like this is how we would change the period of a sine or a cosine. Remember what I told you, what happens to sine and cosine. If you put a 2 there, then you must have 2 complete periods of sine or cosine in its normal period, which is 2 pi. Same thing happens for tangent. When I change this thing to 2, now I have double the s's in a given known period. If I change it to 3, then I'm, again, increasing the frequency. I'm increasing the number of periods that are in kind of like the standard tangent function. If I go up to 4, if I go up to 5, all I'm doing is increasing the frequency, increasing the number. If you go back to tangent of 1, you can see that one period goes from negative pi over 2 to positive pi over 2. This is one period right here. So if you look inside of this region from negative pi over 2 to positive pi over 2, what do I have here? From negative pi over 2 to pi over 2, now I have a complete curve here, and then from here I have this upswing of a curve, and then down over here I recover the other half of it, which is kind of like this downward side, which you can sort of mentally add it with this over here, which makes another period. So you have one full period in here, and then you have half of a period here and another half of a period here. So all of that adds together to give you 2 full periods inside of a standard tangent period, which is, remember, pi, not 2 pi. So if we go to tangent 3x, now between negative pi over 2 and pi over 2, we have 3 full s's. There's 1, there's 2, and there's 3. And then it just continues on from there. So the higher the number you have for the frequency, the more of these things you have to fit into a standard period for a tangent function. And then now we have to switch to cotangent. So we've done how to shift the tangent function. It's exactly the same business for the cotangent. If we have a cotangent of a function and we add a number on the outside, all it does is shift it up and shift it down, exactly as you would suspect. That number just shifts it up or shifts it down. If we have a cotangent function and we change the multiplicative constant out in front and make it bigger, all it does is make it steeper, but it still approaches infinity and negative infinity, same as it does. If you make it a negative, then the thing flips over, just like you would expect. And then if we change the frequency here, then notice that the cotangent function has a period of pi. This is one cycle in a 1 pi region. If I change this number to a number 2, now I have 2 cycles that fit in a 1 pi region. If I change it to 3, then 3 of them have to fit in a 1 pi region, and so on. So take it from the top as far as the shifting goes. This, and then we'll be done. This is a tangent function, right? If you add a number on the outside of a tangent function, it goes up, it goes down. Let me switch to cotangent. We'll do them a little bit out of order here. Here's exactly the same thing. If you have a number out in front of a cotangent, if you add a number to it, it goes up or it goes down, depending on if it's a positive or negative constant. If you have a tangent function and you change the multiplicative constant out in front, make it bigger, then you're making the thing steeper. And if you go negative, you're flipping the thing around. That's all you're doing there. Let's go to the cotangent and see the same thing here. If we change the multiplicative constant in front of a cotangent, then what we're doing is making it steeper, steeper. If we go down the other way, we flip it around. And then finally, the last thing we have is the tangent function. When we change the number in front of the x, then we just change the frequency, the number of cycles that have to fit inside of a 1 pi region. Exactly the same thing happens for the cotangent function. All right, so we change that, and you see you have more cycles in there. All right, what I'd like to do now is I'd like to stop the computer demo, jump back to the board, and then we'll draw some more sketches and try to understand a good way to easily remember what these graphs look like. All right, welcome back. I hope you enjoyed the computer demo. I really find that interactive things like that can really help with seemingly complex concepts. And believe me, the tangent function, it looks funny the first time you see it. There's a lot of little weird things about it, all right? What I want to do now is somewhat review what we did on the computer, because there's some value in me drawing it myself that'll encourage you to draw it yourself. But you should have hopefully internalized what you saw on the screen there and at least have some idea why those curves have the shape that they do. Now what we have to do is just practice graphing them and then solve some problems in the next lesson. Now before I actually do any graphing, I want to remind you why we know that the tangent function is equal to the sine of a angle divided by its cosine, right? And that goes back to the unit circle, right? We know from triangle, trigonometry, we can superimpose anything on a unit circle. So what I'll do is I'll just make this a unit circle. And what we'll do is we will just make a triangle. And this triangle is a right triangle, like this. Now what we have learned, this has some angle in there. And this angle, we can call it theta, but since we've been using x, I'll just call it x for the angle, right? Now, what is this side of the triangle? What is that? Well, this side of the triangle, it's the vertical side. We call it the opposite side because, back in geometry or trigonometry, you learned that the tangent of some angle, you can put x or theta, whatever you want to label it, is equal to the opposite over the adjacent. But what is the opposite side here? The opposite side here of this triangle is, this is the sine of the angle x, because the sine is the projection of this hypotenuse on there. And the cosine is this side right here, cosine of the angle x. That is by definition, the lengths of these sides of this triangle. So the opposite side is the sine of the angle, and the adjacent side is the cosine of the angle. So probably one of the most useful identities that you really have to know is that the cosine of any angle is equal to the sine of the angle divided by the cosine of the angle. That's why I was showing you the two curves in the computer, and I will show you again in printout, because to find the tangent, all we do is literally locate the angle on the sine curve, figure out what the sine of the angle is, figure out what the cosine of the same angle is, and divide the numbers. That produces what the tangent curve is. All right? So let's go, what I'll do is I want to show you the printouts, which is almost basically the same thing we've done there, but I like gesturing and drawing. And then I want to sketch them by hand, because I want you to get a good feel for how to draw these things, without using a computer. So here is a sine curve. Starts at 0, goes up to 1, down through pi. Over here, one cycle, don't forget, takes 2 pi. Period is 2 pi. Cosine, on the other hand, starts up at the number 1. Its maximum, minimum was, of course, -1. Back up to the starting point again. Its period is 2 pi. So the period of sine is 2 pi. The period of cosine is also 2 pi. We should know what those look like because we've been dealing with sines and cosines for a very long time now. Now, to figure out what the tangent of the angle is, at any given point, you locate the angle, whatever angle you want. Let's say you want this angle here. Halfway between here and here would be pi over 4. How would you find its tangent? You would locate the value on the sine curve, and then you would come down here and you would locate the value on the cosine curve, and you would literally take the number that you got for the sine and divide it by the number you got from the cosine. So let's do that real quick and see. I'm not going to grab a calculator, but let's just see what would happen. Well, this is a positive number, and then right here, this is a positive number, so we're going to get some positive number. Let's see what it actually is. When we go onto this graph, at pi over 4 radians, we get a positive number. So it's right here. This location here at pi over 4 radians, which is between 0 and pi over 2, is right here. Let's say we get a tangent back, which is exactly equal to 1, by the way. What is we know what pi over 4 is, right? That's 45 degrees. What is the sine of pi over 4? Square root of 2 over 2. What is the cosine of pi over 4? It's square root of 2 over 2. It's the one angle where the sines and the cosines are exactly the same. So that one's really easy, right? So what's the sine of that angle divided by the cosine of the angle? Well, it's square root of 2 over 2 divided by square root of 2 over 2. Sine divided by cosine, you get 1. So the tangent of pi over 4, which is 45 degrees, is 1. Because the sine and the cosine give you the same value there. So if we go at this graph exactly between here and here, I mean, pretty close to right there, you go up here and read it off, you get 1. The tangent of 45 degrees is exactly 1. But what happens as you keep increasing the angle? When you get closer and closer and closer to pi over 2, what's going to happen? Well, the sine is going to be getting bigger and bigger and bigger, reaching a maximum right here. So that's okay. But the cosine, as you increase the angle, is going to be getting smaller and smaller and smaller and smaller, eventually getting to 0. Now, you can't really divide by 0. But when you get very, very close here, then you're dividing by a number that's basically infinitely close to, as you approach 0, the numbers get very, very small, right? Like getting close to 0, you might have 0.1, and then you might have 0.01, and you might have 0.00000000001. Well, you're going to be dividing by that number very close to 0, and it's a positive number because you're approaching from the top. So if you take the sine, which is very close to 1, and divide it by the cosine, which is very, very small but positive, then you're going to get a very, very big positive number. And that is why the tangent graph goes off the chart up to what we call positive infinity. But it really can't reach infinity. Infinity is not a number. Infinity is just a concept. It's an infinitely large thing in the positive direction. So what we do is we just cut the graph off and say, okay, this thing goes infinitely far up that direction. Now, we eventually do arrive at the angle pi over 2, and since the cosine of pi over 2 is 0, we can't actually divide a number by 0. It doesn't work. You will be calculating until the end of the universe. So let's just skip over that value and go to an angle a little bit bigger than pi over 2. So now the cosine returns something Again, really, really small, close to 0, but it's negative because it's down here. So then the sine on the other side of this angle is going to be still very close to 1, and the cosine is going to be negative, but very close to 0. So you'll be dividing by a number divided by almost 0, but it's a very small negative number. You'll be dividing by negative 0.000000001. And so you'll get a very large negative number. So then, when you jump on the other side of this discontinuity, essentially, and you on the other side of this angle, you get a very large negative number, and that is why the graph shoots off down to the negative side. Now, what you see in books a lot is we draw little vertical asymptotes here, just to kind of like remind ourselves that the function approaches this but never gets there, like this. And you can draw another vertical asymptote here. Now, on my little computer graphing, it didn't draw that, and you don't have to draw it, but I mean, you just see it a lot. You could draw another one here if you want to. But that's why the graph looks the way it does, because when you get to some angles where the cosine, because you're taking sine divided by cosine, where the cosine returns a 0 value, then you're going to get infinity. But as you jump from one side to the other, what's going to happen is it'll give you very large positive number, and then on the other side give you a very large negative number because of what I told you about, because you're crossing through 0 from positive to negative territory. So the discontinuity is like this, and so there really is no value of the tangent function defined exactly at pi over 2, but on either side of pi over 2 we know it does this. And the same thing happens at 3 pi over 2, because what is the cosine of 3 pi over 2? Go back to the unit circle. Here's pi over 2, 2 pi over 2, 3 pi over 2. What's the cosine of this angle? It's again 0. You can see here's the sine of 3 pi over 2, but the cosine of 3 pi over 2 is again 0, so you're dividing by 0. So when you get over here, same thing, you're dividing by 0, but exactly the same thing. On one side of 0 and on the other side of 0, it's going to return a very large positive number and a very large negative number, so you have, again, a discontinuity here, and you have these asymptotes. So when we look at this thing, we ask ourselves, this is a periodic function, even though it's funny and it has these asymptotes, just like the sine and cosine are periodic functions, this is a periodic function also, because the definition of a periodic function is a function that repeats itself. And the tangent and the cotangent functions absolutely do repeat themselves. You can see it happening here. It goes here, and then you call that one cycle, and then you start over again, because you start over at the same values here, and you go and do it again, and you start over again, and if we continue the graph, it'll go on and on forever in both directions like this. So it absolutely is a periodic function. Just because it has these asymptotes doesn't change that at all. So then we ask ourselves, what is the period of the tangent function? How long does it take to repeat itself? And we can say, well, we can look anywhere we want, but we can look from here to here. What is the angle between pi over 2 and 3 pi over 2? If you don't want to do the fraction arithmetic, this is pi over 2. This is 3 pi over 2. This is a distance in terms of angle of pi. So you can see that the angle here is pi, and then you can see it here, negative pi over 2 to positive pi over 2. This is a distance in pi as well. So basically, we have one cycle happening after every pi, so the period is equal to pi. So the period of a sine and a cosine is 2 pi, and the period of the tangent and the cotangent is 1 pi. Right? I keep mentioning that because that's probably one of the main things I want you to try to remember. I cannot say in my life that I've ever been under the gun to produce a tangent function. Sines and cosines, sketch it all the time. Super important. Tangents, yeah, sometimes, but it's not the most critical. I mean, it is important, but it is not the absolute most critical thing that I've ever had to do in my life. But what is very useful to know is sines and cosines, period, 2 pi. Tangents, period, half of that, which is 1 pi. Okay, so that's why I'm kind of emphasizing it. So then we ask ourselves, what about the cotangent function? The cotangent function, right? So remember, I taught you something a long time ago called the trig rainbow, right? You can write it like this. You write it just like you remember it. Sine, cosine, tangent, cotangent, and then we have secant, and then we have cosecant. And what you do is you arrange these things together, and this helps you remember how these things are related together, like this. And what you can see from the trig rainbow is that, for instance, cosecant is 1 over the sine. And, cosine is 1 over the secant. We'll get to those later, but what we can see, tangent and cotangent are linked here. So what we can see is the cotangent is equal to 1 over the tangent, right, of whatever angle it is, so x, let's say. But we know that the tangent is sine over cosine. So 1 over sine cosine. And when we flip it over and multiply, what we can also say is the cotangent of an angle is equal to cosine over sine. So this is just another identity, right? So you can think of the cotangent two ways. Just like you can think of the tangent as sine over cosine, you can think of the cotangent as cosine over sine of the same angle. You just divide them, right? But you can also think of it as just being the inverse 1 over the tangent function, because those are exactly the same things. So if you wanted to reproduce a cotangent curve, cotangent, just like for tangent divide sine divided by cosine, you could go to cosine and then you could divide it by sine. You would get all the correct values, right? So let's do that just for one of them. Cotangent divided, cosine divided by sine. 0 here at pi over 2, 0 divided by, what do we get for the sine? 1. 0 divided by 1 is 0. And at pi over 2, we see the cotangent function passes through 0. It also goes to infinity right here. Why is that the case? Because over here at the origin, the cosine is 1, but the sine is 0. So 1 divided by 0 gives you infinity, and so that's why it approaches infinity. And the reason, of course, for the discontinuous jump is the same exact reason, because when sine gives you 0, as sine crosses from positive to negative, it's going to give you positive infinity, negative infinity. So basically, the curve looks exactly the same. However, it is a little bit shifted with respect to the cotangent. If you notice, we have a vertical asymptote right here, and we have a vertical asymptote. I don't really need to draw it. I don't want to clutter it, but we have one right here. I guess I'll just do it right here. So whereas the tangent, you can kind of think of it starting at negative pi over 2, going up to pi over 2, and the cotangent starts kind of at the y-axis and then goes down like this here. But the period is still pi. This is pi, and this is another pi. So the period of the cotangent is equal to pi. All right? So cotangent and tangent and cotangent, of course, are related to each other. Now, I just taught you that cotangent can be thought of as cosine divided by sine. Take cosine value, divide by the sine value, and you can get it. But we also know, we just said that cotangent is 1 over tangent from the trig rainbow. So another way to think about the tangent curve is just to look at the cotangent curve, is to look at the tangent curve and invert it. It doesn't mean flip it upside down. It means take 1 and divide by whatever value you have. This on the tangent curve is infinity. 1 divided by infinity is 0. So at this point, we get a value of 0. What about right here at pi? 1 divided by a value of 0 gives me infinity. That's why it approaches infinity down here. And these intermediate values are the same. Let's say this returns a 1 right here. At pi over 4, it returns a 1. 1 divided by 1 is 1. So it should return a 1 right here, and it does. All right? And of course, I don't find this all that useful, but I will show you just because it's in some books that you can plot these on the same graph and see kind of how they're related to each other. The tangent function starts from the downward part and goes up through the origin and then up to infinity, and then down through 0 and then again up through infinity. The cotangent function crosses where the output is equal to 1 and then goes down to negative infinity as well. But you can see they're sort of shifted with respect to one another. This is a little messy for my taste. What I want you to do is try your best to remember, number 1, that the period of the tangent and cotangent is pi. That's the most important thing. But the second most important thing is to try to remember where to start drawing it. If I have to ask you to draw a tangent function, what are you going to do? I want you to start at negative pi over 2 and then draw it going up. And for the cotangent function, it starts the other direction, high to low, and it goes from the y-axis here down here where the other asymptote is over there. All right? All right, so now what I want to do for the very end is we're going to try our best to sketch these without using, basically without using any of this stuff. I mean, yes, I know logically that the tangent function is sine divided by cosine. And I know all of that stuff, but when I sketch it, I'm not going to be dividing numbers. I need to know how to sketch it like the back of your hand. So I want you to get some practice with that. So what we're going to do is we're going to sketch the tangent function. And then we're going to sketch directly underneath it the cotangent function. Is it going to be perfect? No. That's okay. I want you to do this yourself also. So here we're going to have tangent of x, which we know is equal to the sine of some angle divided by its cosine. Whoops, of the same angle. All right? Now, what do I label for the x-axis? So I'm going to do the same thing I always do. This is 2 pi. Half of that is pi. Half of that is pi divided by 2. And then over here we have 3 pi divided by 2. Now for the tangent function, I remember and I know that I always start drawing from negative pi over 2. That's the only thing you really have to remember, right? And I need to draw my asymptotes, and I'm trying to get you to remember this stuff. So I want you to remember that the tangent function starts down and then up, down and then up, down and then up. That's what I really want you to remember, okay? So you then know that your asymptotes kind of have to be here, right? Because that's really the only way that you're going to be able to get a down, and don't forget you have to go through the origin, and then up like this, right? And then the same kind of thing going on over here. So I'm going to have an asymptote right here as well. And then it repeats itself. It goes down, it has to go through pi right there, and then up. And then I can start repeating again, down, and goes through the origin. Whoops, that's not quite right, but at 2 pi. And then it goes up, and then if I can continue labeling over here to figure out where that's going to be. But what I want you to remember is that the tangent function starts down through the origin, up, down, and then up, down, and then up. And then you just have to place these asymptotes because I've drilled into your brain that the period is pi. So you start at negative pi over 2, you mark your next one at pi over 2, and then you just keep marking after that, and then you just down, up, down, up, down, up. That's what a tangent function looks like. That's what I want you to do when you sketch it yourself. Now for the cotangent function, we're going to do something very similar. Of course, I could look at the graph above, and I can say 1 divided by all these things and all that, but I want you to get faster at it. I want you to write the cotangent of a angle, which is equal to 1 over the tangent of the same angle, which is equal to cosine of the angle divided by sine of the angle. Two different ways to think about the cotangent function. So I'm going to do the same thing. I know that the cotangent doesn't start at negative pi over 2. It starts right next to the origin right here. So I'm going to label, I'm going to try to put it in the same places. Here we have 2 pi. Here we have pi. Here, right here, we have pi divided by 2. And then right here we have 3 pi divided by 2. And I know, because I remember, that the cotangent is going to start up and then it's going to go down, and the period is pi, so I know I'm going to put an asymptote here. And the period is pi, so I know I'm going to put an asymptote here. And then I remember that it starts high and then goes low, so it's going to go up here, it's going to go right through this point, and it's going to go like this. It's going to start high, I'm going to go right through this point, and it's going to go like this. And if I wanted to continue, I would continue like this, but I haven't labeled my axis like that over there. So let me make sure I covered everything in my notes. Period is pi. Sine and cosine in contrast are 2 pi periods. Asymptotes of the tangent and cotangent curve are not in the same place. That's another common thing that people get confused by. The asymptotes exist because the denominator goes to 0. We talked about that because basically when the sine function goes to 0, it's going to drive this to infinity. When the cosine function goes to 0, it's going to drive that to infinity. That's why the asymptotes exist. And I think that is actually all I want to say. So again, tangent, cotangent. You can take the sine and divide it by the cosine. You get something called the tangent graph. Start at negative pi over 2 and go up. Then you go up, then you go up. Alternatively, if you want to look at cotangent, you flip it around, cosine divided by sine, and you recover this graph, which starts near the axis, and then start high, go down, start high, go down, but in both cases, the period is pi. I'm drilling that in because it helps you lock in your asymptotes and so that you could sketch this thing. And also you remember that the tangent function you start drawing from negative pi over 2. So when you sketch it, you start over here and you go up, and then when you do the cotangent, you start at the axis and go down. So hopefully you remember that, but honestly, if you don't, if you know where it comes from, if you know why it comes from sines and cosines, sine divided by cosine or whatever, that is the most important thing, because then after that you can reconstruct and understand. You'll be miles ahead of most people. A lot of people look at the tangent graphs, they have no idea where they come from. Why do they look that way? Nobody knows. That was mainly the important part of the lesson. Now in the computer demo, I also talked about how to shift these tangent graphs, and hopefully it makes sense to you because it's very similar to the sines and the cosines. So what I'd like you to do now is watch this lesson again, make sure you understand it. In the next lesson, we'll start sketching tangent and cotangent graphs where we shift it around and make other changes to the baseline graphs.